Good day, ladies and gentlemen. My name is Casper Durandt. My paper today is titled Improving Production Line Efficiency by Identifying the Root Causes. And I hope to demonstrate to you a new, unique way, something you've not seen before, on how you can improve your production performance. My interest in this paper, to declare my interest, is to be the development and enhancement of the theory of free time and the additional development of this theory with new people wanting to do research on this topic. I will therefore also provide my academia page for information so as for scholars who want to do further development and seeking commercial solutions for this theory are welcome to contact me. So I'm going to introduce the four-letter acronym PUFT. The three-letter acronym stands for the productive use of free time. I've been working in manufacturing for most of my life, probably around 28 years now. And I have extensive experience in world-class manufacturing in Japanese techniques like Kaizen and Kaikaku, also TQM, Poka-yoke, Lean, autonomous maintenance. So there are many of these manufacturing techniques that I've been exposed to. But I've been particularly interested in Kanban initially, then just in time, and then the theory of constraint. And it's in studying the theory of constraint that I stumbled upon this idea of try to utilize the non-constraint. So what is PUFT? So PUFT is a system that uses software and it monitors the bottleneck on a production line. So there is always a bottleneck, either a design bottleneck or a stochastic bottleneck developing as the production line changes through breakdowns, material changes, methods, etc. And what PUFT does, it calculates the location and magnitude of free time. So you can think of it as the theory of non-constraint. So traditionally a production line is designed in a V profile, meaning production machines prior to the design bottleneck can run much faster than the bottleneck machine. And this is for good reason. Engineers designed the line like this to protect the bottleneck machine against stoppages caused by either starvation or buildback. So in the PUFT calculation, it uses all of these over-designed machine speeds to actually spell out to the production operator in real time where does he have slack or free time that he actually can use to do something else, like autonomous maintenance or cleaning, something that they can do right there and then. So what is the primary objective of PUFT? So the primary objective of the solution is to improve efficiency of production lines. That is it. And by improving production line efficiency, you improve productivity, you reduce production cost, and you delay the capital capacity projects, meaning you get additional capacity because of an efficiency and you won't have to buy the new production line this year, maybe only next year. So where does PUFT come from? So it is the result of a formal PhD study that was done in South Africa, and I've added here the link to my thesis. The thesis is also available on my academia site, where I go into huge depth in the mathematical deterministic calculation of the free time. But in essence, it works on the principle where you divide in real time current speed into accumulation quantities during various line states, whether it's startup, whether it's solid running, build back, starvation, or run out. And each one of these phases are clearly described for the different types of production lines, whether you have a V profile or a single profile. So you're welcome to leave your comments also in the academia page. So what about other applications? So PUFT works well with other applications. So don't see it as an or solution, it's an and solution. The idea is to have a production support system for the level 1 operator, the operator that is on the production line, working on the shop floor, dealing with the production machines in real time. It's not a regular supervisory control system. It's not like SCADA. It's a lot more interactive by the operator, and it shares real-time data, and it also shares something about the future. And I'll talk a little bit around that later in a later slide. It can operate as a standalone system, meaning if you have nothing, you can implement the system. It's very basic, and I'll explain a little bit later in the presentation what hardware requirements are necessary for the application. And then finally, if you look at the pyramid of the levels in the organization, typically PUF would be for level 1. This is the operator working on the shop floor. SCADA would typically be for supervisory staff that works day shift only, and then the enterprise management system, such as SAP, is a system that is used by more senior staff in the organization. So I want to introduce the Genzai principle, which is now in Japanese. It means to act now. So the resulting benefits from PUF is only available if we act now. I like to call it, you know, we move the incident from the mortuary to the emergency. So what we're saying is that when we sit tomorrow morning and we do a Pareto or daily performance, we're basically looking at the dead body. You know, what went wrong? Whereas we need to move the incident to the emergency room. And how do we do that? So this is where PUF unveils uncertainty to certainty and give you a glimpse into the future. So to put this into perspective, if this is the present and this is the future and this is the past, the typical applications that we use to analyze the past would be real-time efficiency. Now, real-time efficiency is already a function of the past, because it gets measured from 6 o'clock in the morning. If it's now 10 o'clock and the efficiency indicator says we are on 72% indication, we're already looking at history. It's not no longer the present. Daily performance charts comes after the event. Trend analysis, the SCADA systems and infrastructure planning already give information for in longer time periods. But when you look at PUF, it actually tells you that your production line or this production machine has 40 minutes of free time. So meaning for the next 40 minutes, you are free to do anything you want with the mind, meaning you can see into the future that the next 40 minutes are available. So, and it's the trick of utilizing that free time, that slack, while not affecting the bottleneck that will improve the productivity and efficiency of the production line. So here is the definition of free time. It's the time available for a production machine operator to stop his machine due to inherent spare capacity or due to a stoppage on the current line constraint without affecting the overall performance of a coupled manufacturing production line. But let me unpack this. It's available due to two factors. One is, as I said, the free time comes from over-design. Machines are running twice as fast as they should be able to keep up with the bottleneck machine. So this machine runs and stops and runs and stops. There's a lot of accumulation in between. If you do the calculations right, you will know exactly how long you can switch this machine off and exactly when you need to switch it on for it to catch up and not stop the bottleneck. So that's the first type of free time. It's dynamic. The second type of free time is this, where it says, or due to a stoppage on the current line constraint. So for example, if the filling machine is the line constraint, if the filler has to stop to do a flavor change or they have to fix a valve, that information, if you bring that information to the other production machines, they can add that additional free time to their dynamic free time. And that is how this free time, if every time you stop the filler for a change on materials or a change on brands, and you say to all the other production operators, listen, you have an hour now, do that autonomous maintenance, but do it now. This is the Genzai principle. Act now, make it happen. This body is still in the emergency room. And then last point is coupled manufacturing production line. If it's not coupled, if it's not a coupled manufacturing production line, the free time theory doesn't apply. It's got to do with calculating time by dividing throughput into quantity on all the accumulations. What can we do with this free time? So the aim is to use the free time effectively and productively. As I said, such as doing maintenance, cleaning, and inspection on the machine without affecting the line efficiency. So as a result, the overall production line efficiency will also be improved. Here is a typical screenshot of what this could look like. So here in this example, we have a filling machine, then a labeler, a 6-pack packing machine, a caser, a palletizer. We have a stretch wrapping machine and a bridge to the warehouse. So for example, if the filler is running, it would show orange like this, and it will show 0 free time because it is the current bottleneck, meaning if you stop this, filler efficiency will be affected. Whereas if you can stop this labeling machine, see there's 30 minutes of accumulation between the filler and the labeler, meaning there's a huge accumulator between the filler and the labeler. And if the labeler stops now, you can fill that accumulator to the filler, and it would be 30 minutes before it's completely full, and it will actually stop the filler. Whereas if you start this labor after 30 minutes and leave 44 seconds, there will be enough time for the labeler to start pulling the accumulation on to keep the filler running continuously. So that is how the free time is displayed. It's displayed in minutes and if we put the laser pointer there, is hours, minutes, and seconds. Dynamic free time typically is minutes, where static free time, when you have a breakdown, that can run into hours. So for example, if the filler now has a breakdown, the operator sees, well, we've had a major valve failure or a motor burn, he's going to have to change the motor. He knows it's going to be 2 hours. It's the only reason that the operator need to interact with the device. If you are the bottleneck and you stop, the device will ask, you know, how long are you going to be down? And he will manually put in 2 hours. When he puts in the 2 hours, the 2 hours will be updated on all the other machines, and all the other operators can start working on that maintenance during those 2 hours. Here is a snapshot of the efficiency of a typical production run. Here is the start of the shift, and you can see the beginning of the shift. The machine wasn't running for about 20 minutes. Maybe there was a team meeting, and you can see the machine starting up, takes running a slow speed initially, and then running full speed. Running full speed for about 15 minutes, then half speed, and then stopped again. We don't know why. You can see the efficiency. First, the efficiency is 0, and only once the machine starts running, you'll see the efficiency start going up quite quickly, because you have a small denominator in the beginning of the shift, and there you can see the efficiency dip for some reason and going up as the line runs at full speed. You can see then numerous other things happen. You can't really explain why the efficiency ended up at 72% if you look at this sheet only. If you look at this graph, this graph now depicts all the production machines. So what the PUF system does, it actually, because it calculates free time, it actually calculates the machine with the smallest free time as the current bottleneck. As conditions change on the line, the bottleneck moves around stochastically. The free time system calculates it all the time, the current bottleneck and the position of that bottleneck. And from that, it can blame the correct machine for the efficiency loss. So without any operator intervention, the free time system will tell engineering in the morning on the Pareto analysis that we have had the following machines affecting efficiency. And in many cases, production machines affect efficiency, but it's not obvious. The production machine affecting efficiency could be stopping, every 5 minutes for 20 seconds. So it might be a ongoing quality issue, but it never stops for long enough to be noted in the breakdown record. But in the meantime, that build-back runs through to the filler, and every half an hour, the filler stops for a short while. So if you look at this graph again, you can see, why did the filler stop in this case? So if you look, and you can see, it's this red one, it was the 6-pack. So but it didn't stop long enough to warrant a breakdown. a record to be made so that the engineering guys would attend to it. And similarly, if you look at the Kaiser here, Kaiser, many very small stoppages, never really for long enough to warrant a reason why engineering would investigate. So what the PUF system does, it manages to find those small stops all the time and add them accumulatively, so that at the end of the day, you will really know which machine was the actual cause for the efficiency loss. This is a huge difference between what we can get from manually captured breakdown systems. This is an automated system that, through the algorithm of free time, calculates automatically for you your Pareto analysis, and it's 100% accurate. So there's no unaccounted percentages. So, for example, if your efficiency was 73%, the 27% lost efficiency will be indicated to you which machine was it that stopped the filler or your bottleneck machine, and for how long. So there is no more guesswork when it comes to your reporting. There's one level down, as you know, assignable causes. So what you can ask the operator to do is, when he has a breakdown, he has to assign a cause. And there's a drop-down menu. You just pick which assignable cause you want to add there. That gives you the second why of the 5 why. So why did we lose efficiency? It was the six-pack machine. Why was the six-pack machine broken? We didn't have film for an hour. There was a logistic issue, whatever the case may be. Quickly, just the hardware for the system. The PUF hardware consists out of a small PLC, which gets placed into the electrical panel of the machine. It gets wired to a pickup device that's either connected or connected to an existing, preferably, without interfering with the signals on the line. There's not allowed to touch any of the signals on the line, or any of the ladder logic, or any of the PLC logic. That stays secure. Don't touch by PUF. These signals gets used and calculate some ladder logic locally, and then coded and sent to the cloud. Cloud computing does every 5 minutes the resulting free time for all of the machines, and it would place back on the internet. And in real time, one can monitor what goes on in the line, and that information is shared with the operators as they work during the day to do the GenZai work. Just on a case study, here 2 examples. So in this example, the PUF system was installed, and the operators were trained, and once everything was ready, there was a day on which the project started, and they switched it on the day. And you can see a marked improvement in what is already a very erratic efficiency. The reason why this efficiency is so erratic on this line is it carries a huge number of SKUs. So many shifts is really just pack changes. So this is more a line utilization matrix rather than a line efficiency matrix. On this one, you can see a slow improvement over time. In this case, the system was switched on from the start, and as operators get trained and as they use it more and more, you can see the improvement of the efficiency. This is a typical Kaizen improvement, one of continuous improvement, where this one is what we call Kaikaku, which is a step function improvement, typically what you get when you introduce a new technology. Then finally, here is the academia page. Welcome to visit the page. On the page, you will find the full thesis, and please, for scholars that want to participate in the discussion on the free-time theory, welcome also for prospective students in master's and in doctorate degrees that want to further develop the theory. There is lots of scope for this. Also, I've added a link here to a YouTube link just describing how the system works in a more animated way. I thank you.